welcome to the HKS Energy Policy Seminar. It's our first meeting of the semester. I'm Joe Aldi, and I'll serve as the host. Thrilled to have so many colleagues and students and fellows and friends joining us in the room. And thanks to everyone as well who's able to join us online via Zoom. Before we get started, let me open with a few notes of appreciation. We are grateful for the support of the Belfer Center, the Mosfar Rahmani Center, and the Salata Institute for Climate and Sustainability for their support of this seminar. I'd also like to express my sincere appreciation for Liz Hanlon and Ricardo Mora for their support of this seminar. Our good friend Paul Sherman recently retired. And Paul, if you are spending part of your retirement on Zoom watching this seminar, thank you for everything you've done for us over the years to support our work on energy and climate. We're thrilled to have with us today our colleague, Professor Charles Taylor, for his talk on land conservation and the clean energy transition. Charles Taylor is an assistant professor at the Harvard Kennedy School. He's an environmental economist who focuses on climate, agriculture, ecosystem services, and migration. Before joining us at Harvard, Charles was a CRC Wantrup Fellow at UC Berkeley. Before academia, he worked at McKinsey & Company, the Bill and Melinda Gates Foundation, and the Earth Partners LP, a land and environmental investment company. He has a BA from the University of Virginia and a PhD in sustainable development from Columbia University. Now, many of you will recognize Charles because he's a regular attendee of this seminar, and it's great to have him here with us today in person to present. I'll note that Charles will take questions throughout the seminar, so feel free to pepper him with anything that comes to mind. Over the course of the seminar, we will also reserve time at the end for Q&A and comments from the attendees. Charles, as a speaker, welcome to the Energy Policy Seminar.
Thank you for everyone to come out here. I'm going to talk about land conservation and renewable energy, and this is new work, so I'm excited to share it and get people's reactions and their feedback. And it's joint with Meredith Fowlie at Berkeley. So we're in the midst of a clean transition, as all of you know, and this is going to require a huge amount of decarbonization and a build out of clean energy infrastructure. And this can both deliver greenhouse gas emission reductions, and it can also deliver potential economic growth opportunities. And kind of one underlying thing about the US is it's blessed with abundant renewable energy resources, wind and solar. So there's more kind of theoretical capacity there to do it. It's a matter of the how and the when and the cost. Though, as you see in this map, this is one kind of prominent projection under the Net Zero America Project for what this might look like. For example, if we went fully net zero in terms of the renewable energy and transmission footprint that we would see in the US. And if you kind of squint, you can see a lot of land is either covered or directly or indirectly impacted by new renewable energy development. So it's a large scale feat, both economically, but also in terms of potential land use implications. On the other hand, we also have this kind of looming, what we'd call like a biodiversity crisis. Globally, it's estimated there's 1 million species at risk, and habitat loss overwhelmingly comes from land use change, right? So while things like direct pollution into water, air, or climate change affecting the range of species has some impact, overwhelmingly it's a loss of habitat, of loss of natural areas from becoming developed or cropland or whatever else. And clean energy infrastructure will, to some extent, do the same thing to some degree. So there's this potential trade-off here between expanding clean energy infrastructure to some extent and protecting conservation value, given that a lot of the kind of species value that we see has come from land use. And kind of concurrently with that, both in the US, and this was during the last administration, which this might have been paused, I'm not sure, but there was a big announcement to conserve 30% of the US for conservation and biodiversity by 2030, and this is part of a global UN Convention on Biological Diversity 30 by 30 initiative. And these are big numbers. Directly or indirectly in the continental US, about 12% of the US is protected. You can think of things as like national parks or forests or things that are kind of explicitly development is restricted on. And this goal, whether that be achieved or not, would be to nearly triple that, which would be quite large scale. So we have both a lot more energy and infrastructure to build out, while potentially to deal with our biodiversity crisis, a lot more land to conserve. Right? So in the simplified world, how do we think about this tension? Right? So here's a really simplified schematic where we can say, okay, let's decide where we're going to build a windmill or a solar plant. And does it have renewable energy value, right? Is it going to be a good project and in terms of its economics? And what about the conservation value of that land, right? We have some easy ones. If it's no and no, we're not going to develop anything on it. If it's high conservation value and not good renewable, we're going to conserve it. Vice versa, if it's high renewable value but low conservation value, let's develop it. But this kind of red area is where you potentially get into some of the conflict. And you see this anecdotally increasingly. And after the talk, I'd be interested in getting people's takes on this as well, with headlines like this. Clean mega projects divide a surprise group, environmentalists. In some fights over solar, it's environmentalists versus environmentalists. And then a recent op-ed in the Washington Post that environmentalism could stop the clean energy transition. Right, so this idea of a green versus green, of people who are kind of prioritize all things equal conservation, and are wary of the trade-off for climate infrastructure, and those who kind of say like, hey, we have to get climate right, first, and then worry about conservation after. And clearly, a lot of people are balancing both those things in their head, but might fall on one side or the other relatively. And kind of within that, we're seeing a lot of state level movement to try to address these conflicts. For example, being here in Massachusetts, when we think about this, right, what was kind of the dream was to get Quebec Hydro's transmission line down from Canada. And we saw that was really difficult. And who was one of the primary opponents of that? Sierra Club. So there, we see this locally in a lot of the offshore wind projects in Massachusetts as well. And kind of as part of this, states have gotten involved, where there'll be state laws trying to kind of rein in some of the local interests as well as some of the environmental interests to streamline project development so that states can meet their targets of renewable energy development. We've seen this in Illinois, in New York, in California. So it's this tension that I'm going to try to empirically investigate, right? Like, is this true? Do we see anything? What does the data look like? What's out there? And kind of in the backdrop of this, I want to frame what's going on in the overall energy landscape. And a lot of you are probably familiar with this, but there's been this kind of like remarkable, I would say, shift in our energy production. This is electricity over the last decade or two, right? Where we see that this is actual generation on installed capacity. So this is how much electrons are actually getting produced, right? And we saw somewhere around 2020 that renewables surpassed nuclear and coal in terms of electricity production. And I'll note renewables in this bucket also includes things like hydro, but in terms of what's actually driving the growth, that's largely wind and solar. So this paper kind of also in the backdrop of this is trying to get at this question, right? This has been really good progress, and can this progress continue? And one thing to note, right, we had this huge Inflation Reduction Act, and we had a number of legislation meant to kind of like bolster and support the development of renewable energy that may or may not be slowed down in the current administration. But the kind of trend was continuing throughout, across administrations over the last decade or two, right? Renewable energy was increasing, under the Obama administration, as well as the Trump administration, as well as the Biden administration. So, but can this continue? And so this is getting at, like, while we know the costs have gotten lower in terms of the technology costs, this is going to try to explore the question of, is it possible that the land use constraints or the local constraints are going to be the kind of the factor that reduces the growth of renewable energy going forward? And if so, how much? You can think of this, one idea of this is like, this kind of got a lot of the low-hanging fruit land, where we can develop our wind and solar at a relatively low cost and a relatively low level of local opposition. And, is that path going to be harder going forward, even if the technology and the economics are as favorable, if not more favorable, going forward? So these are the kind of three questions in this paper, or this work that we're investigating. First, is there just a tension here? What is the relationship between conservation value and renewable energy value? Then we're going to look at actual conservation policies and see, did this affect renewable energy projects? Like, did this kill them? Did this, and if so, what kinds? And then thinking a little bit about some of the cost benefits of these protections. So a very quick preview of the results. Is there a tension here? Kind of a yes, but a yes and no. Conservation value overall, kind of if we think kind of in the average, is not correlated with how much renewable energy value a site has, right? So that's good in the sense that, like, there's not a systematic relationship where our best renewable energy lands are all the most pristine ecosystems that we want to protect. But at the same time, the correlation is such that, like, a lot of places that are valuable are also low cost from an energy production standpoint. The second point is a very big yes. Existing land use protections, which I'll talk about, things like the Clean Water Act, things like conservation easements, have a significant effect on reducing the probability that a project can get developed and ultimately get an interconnection agreement. And then the third, what does this mean in terms of the overall economics? Are some preliminary simulations show that these policies do kind of shift projects away from development in sensitive areas and don't have an obvious impact on overall investment costs, which would be a kind of a potentially positive outcome, but that's more preliminary. So first, let's investigate this correlation. How do we do this? So a little bit, I won't really go into this here, but economists have been thinking about renewable energy investments and policies that can support them, including some work by Joe and co-authors here, right? Like, renewable energy support can take lots of form: investment tax credits, production tax credits, right? And this is a policy decision of, if you want to spur development, what is the best mechanism to do that? On the other hand, there's a relative, a kind of a body of work that looks at the economics of land conservation, and then aside from economists, energy modelers are beginning to think about land protections and land constraints when they think of the large capacity expansion models. So when you think about, if I need to go from this capacity of electricity to this, where am I going to put it? In addition to taking into account project economics, how do I take into account land use and conservation concerns? And that's just kind of, I'd say, beginning with some recent work by Wu et al. And so we're going to dig into this. So I for the sake of this presentation, I won't really go into the model or the math here. I see some of my students from API 201. I could test you. But so what we're going to do is just make a really stylized, simple model of renewable energy development, where we're going to say, for any given site, what is the potential electricity it can produce? And that's going to be Q, and it's going to be a function of just, how big is it? How many megawatt hours is it? Is the installed capacity? What's the curtailment rate, right? Like, how often can you not run the windmills because there's not a market to sell into? And then also its capacity factor. How often is there the resource available for it to run, We're going to assume zero marginal costs. And then we're going to define a site technology vintage specific LCOE. So this is the levelized cost of energy is a metric you'll hear a lot in this literature. It's pretty much an attempt to make an apples-to-apples comparison of how cost-effective a given renewable energy or any energy project is in terms of dollars per megawatt hour of energy produced, taking into account what's the upfront capital costs also, and taking into account the annualized operational and costs and revenue. So we're going to just do that, and we're going to run this analysis for all the projects that ever entered the interconnection queue, which I'm going to talk about a little bit later in the paper, but pretty much projects who want to sign up for the potential right to sell into the grid. So these are like projects that are serious and saying like, I think I have a wind or solar project that I want to develop. I'm going to get in line with the local authority and start to apply for these permits. And what this looks like is this is kind of on the x-axis is the cumulative capacity in terawatts. And on the left is the kind of cost of the project. So lower cost projects, these are like really good wind, really good solar, really close to where you want to sell it. These are really efficient economic projects. As you kind of go up in the lines, those are more expensive projects. Right? And kind of what you'll notice, you might have heard about this in terms of analysis of the interconnection queue, is that when we put together wind and solar, there's been over 2.5 terawatts of electricity in the queue, right? The entire US electricity grid that we currently have of all energy types is 1.3. So there's this massive amount of backlog projects that like want to get developed out there that are in the queue that are nearly twice the existing capacity of US electricity grid right now. Active in the queue, right? We have about 0.4 terawatts of wind and about 1 terawatt of solar, right? So very big numbers, only a fraction of those will come through. And we're gonna then say, okay, that is how you would model it from just an economist standpoint without taking into account land use or environmental or conservation constraints. But what if we add this H term, right? So let's think of that as the conservation value of a site. That we can think of this as like, what's the value if we didn't develop this site into a windmill or a solar project, right? And if we could somehow monetize that, right, we could incorporate that into our cost, right? Almost like an externality that we could incorporate into our estimate of the cost of this project, right? Just as we would have a CapEx cost, we'd have this conservation cost. But these are really hard to do, right? So we can use proxies for them. And there's lots of different, what's the conservation value of a piece of land proxies out there, right? And I'm being somewhat purposefully vague when I talk about conservation value, because there's ecologists have their own definitions, biologists have their own definitions, politicians have their own definition, farmers have their own definitions. So I'm allowing for us to use multiple definitions here, right? And you can think of this in terms of ecological value. I want to conserve pristine forests. I want to preserve wetlands. You can think of this in terms of threatened or endangered species habitat. I want to protect whatever lands where will have the biggest bang for my buck in terms of making sure no species go extinct. Or you can think about this as kind of a more human-centric ecosystem services model. I want to protect lands such that if I pave it, then we won't get the city to flood, right? I want to protect these areas that provide pollinator habitat for agriculture, right? You could define this along multiple dimensions. We're going to use one, for example, along with many others from the Nature Conservancy, a prominent environmental NGO. And they have these maps that show how it varies across space. And if you know the continental U.S. and the landscape a bit, you might notice some things, right? There's a lot of wetlands up in northern Minnesota. This is kind of the biggest remnant prairie in the U.S. in eastern Kansas, the Flint Hills. You see the Everglades down there. So it's incorporating a number of those things into this index. And then if we just map that on to every single site of these 20,000 projects that ever someone tried to develop for energy, what does the environmental value of these look like relative to the levelized cost of energy for them? Right, so this black line is what you saw before. This is just pooling all wind and solar of what they look like in order from the most efficient and lowest cost to the highest cost, including a number of other, what we call like proposed sites that weren't actually developed. And then this green line is the kind of averaged out environmental value. So what you see here is it's pretty flat, right? So it's not that projects on this side, which are really efficient and cheap, right, necessarily have more or less environmental value, right? And so it's kind of flat across. So they're pretty much perfectly uncorrelated. Though, as you can see, these green lines are the actual non-averaged line. So for this given project that is a really low cost, right, it might have an individual environmental impact score of way up here, or it might be way down here. So while on average there's no correlation, there's a lot of projects, that are low cost that might have really big ecological value that we want to see whether existing conservation policies protect. So it's kind of, this is the yes and no answer to this. And if we just kind of plot the correlations of these measures, so again, this is the levelized cost of energy, and these are the various measures we use. I just showed you the Nature Conservancy's kind of impact score of what a wind or solar project would do to a site. We can use other ones, and I'll talk about all these in a little bit. The wetland share, another measure directly of habitat share of the value of sensitive species. Fish and wildlife measures, bird habitat from the Audubon Society. And you'll notice this correlation is pretty much zero, right? So that zero means that there's no systematic relationship between how expensive or cheap a renewable energy project is and the conservation value according to any of these dimensions. And some of these are also quite correlated with each other, right? So for example, wetland share and Nature Conservancy measure are quite correlated, right? The Nature Conservancy is valuing wetlands in the input of their model because wetlands are incredibly important for breeding habitat and a number of species, for example. So with that said, we're going to look at yeah.
So you've done this where you're looking then at a very spatially refined level of the conservation impacts. You haven't said anything about the other externality, like the one we typically think of when we think about promoting renewable power, which is reducing CO2 emissions. And that's going to vary depending on the carbon intensity of the grid on the margin when we put in a new wind farm or a new solar facility, to the extent that's starting to displace some of the incumbent fossil fuel, or perhaps displace new investment in fossil fuel power generation. So it'd be interesting to see from your analysis not only how does that LCOE chart compare with these conservation impacts, but do we see low LCOEs in places where we may get a bigger carbon bang for the renewable investment?
Yeah, that's we could and should do that, and I think to kind of maybe say that back for the crowd is similarly, any given site has a differential value in terms of the amount of emissions of greenhouse gas emissions it will displace, right? If you're building a wind turbine where there's a coal plant, right, and it's going to like use up, replace that, that's different than if you're building a wind turbine where there was hydro, right? So this could also look very variable rather than using our environmental impact score by the greenhouse gas displacement. And we could certainly look at that as one of the other externalities. Great suggestion. Okay, and then in terms of the policies here, there's there's a number of policies that affect land use that you wouldn't necessarily think of them as conservation or land use policies. And kind of first and foremost here, I would say, is the Clean Water Act. And a lot of you might think of the Clean Water Act as that's what kind of cleaned up the rivers, right? That's what kept factories from putting their sludge, and that the rivers used to go on fire, and it cleaned it up. But that is one section of the Clean Water Act. Section 404, the other big one, prevents what's called discharge and fill into waters of the United States. Right? So what does that mean? Pretty much any time you want to cross a stream or fill a small water body, even if it's not water all year round, if it's if it's deemed a wetland, you need a federal permit and going through the Army Corps of Engineers and the EPA to do that. And it can be quite costly, and kind of in practice, in terms of the scale and scope, it's probably the biggest land use regulation that we have in the US. And I have some work with colleagues trying to estimate both the cost of that policy in terms of the opportunity costs of not being able to develop, as well as the value of that policy in terms of protecting wetlands. The other big one is the Endangered Species Act, and that's kind of explicitly there to protect endangered species as defined by the Fish and Wildlife Service, and the habitat in which is considered sensitive, right? And that imposes costs on developers as well as limits that could potentially affect whether a renewable energy project would get developed or not. And then the third one is this category that I'm going to talk a little bit more about, because I think it's been analyzed a little bit less in this literature, but it's something called conservation easements. And this is largely through the Treasury tax code that allows you to protect land in perpetuity in return for some remuneration and tax benefits. And I'll go into that. So we're going to quantify each of these in terms of every single renewable energy project in the US that was proposed, and see how much does the extent to which they overlap with these affect either whether the project ever gets proposed or whether it succeeds. So before I go into any questions, all right, I'll show kind of I like kind of showing the geography of these things, so we kind of get a feel for how big, how material is this, and how niche are these policies. So, and it's always hard to tell like how zoomed in you are. There are wetlands everywhere, but the blue areas show like where the big massive wetlands are. So these are areas that you'd think is like pretty much anything you do near one of these blue things is going to be regulated under the Clean Water Act, right? And it will either outright prevent development on it or make it very costly to obtain the permit, right? And those are kind of a lot of the places but also kind of places throughout the West, which you think of as relatively dry, but have certain water features and seasonal water features that make it such that they are kind of important from a wetland standpoint. The Endangered Species Act, again, has a very kind of big and heterogeneous footprint here. You can see that there's like a number of kind of discrete polygons that are associated with certain endangered or threatened species, but then a lot of these lines, right? And these are often associated with aquatic or bird species that use certain rivers for habitat and breeding. And you'll see there's a lot of variation, right? Kind of in the upper Midwest, there's a lot less. In the Northeast, and then there's a lot in Texas or in California and the Pacific coast. So this is some of the information, the second bucket of information that I'll incorporate. And then the third is this category called conservation easements. So I'm going to spend a minute just kind of describing what this is here. Yeah. Yeah. And this is just a matter of zoom in. I have every point. It's just when you zoom in, you'll see it. But to your point, especially in these more densely populated areas, they're often much smaller. But because of that, they're in areas of land that you often need to either cross with the transmission line or something else. But great point. Okay, so easements, these are legally binding agreements that a landowner, in effect, gives up rights to develop land in exchange for preferential tax treatment, right? So let me kind of give you a hypothetical. Let's say I own a farm that is on the market, would be worth $1 million. I want to keep it from being developed into condos or getting a factory on it into perpetuity. So I either donate or sell my development rights, right? And let's say an appraiser then comes in and says those development rights are worth, you giving up those rights in perpetuity are worth $500,000, right? Then I can take that as a tax deduction that I can claim over time, as well as then benefit from the lower tax basis in my property tax on a lower assessed value. So it's a way to kind of conserve land, particularly on the kind of urban periphery where people are being faced with kind of increasing property taxes and other development constraints, and they don't want to develop it. It's very, very popular. And pretty much easements are the biggest source of conservation land growth by far, right? We're not developing all that much more federal land, federally protected land or state protected land. This kind of private channel is the large one, and we have an easement expert here, Rand, who's done this his whole career. But on the other hand, it's also very, very costly, right? In terms of the actual kind of foregone annual tax revenues that come from this donation, right? Just as you make a charitable donation, you might be able to write that off on your taxes, right? This is a foregone tax revenue from the government. That equates in recent years to about $2.3 billion a year. And then there's potential local impacts in the reduction in property tax. So 2.3 billion in terms of like a lot of USDA farm programs, like in terms of actual money that's going in, is material. It would constitute one of the biggest kind of federal farm programs out there in terms of the dollar value, but it just operates through this IRS channel. And it's also very regressive, right? It disproportionately affects the wealthy, right? People who are landowners, often not far from cities, who at least generally have over 100 acres. The average tax deduction claimed for someone who's donated an easement is $1.2 million. So that's the deduction claimed. But because of that, it's a sweet program, and it's big. Some estimate about 38 million acres of U.S. land. And that's about 2 times the size of the USDA's conservation reserve program, which is kind of a 10-year program to do conservation practices on your land, which is quite popular at about 20 million acres. Okay, so this is what conservation easement map looks like. Again, kind of the same thing, right? If you zoom in, you'll see them everywhere, but it kind of has this much broader and diffuse footprint of where they are throughout the U.S. Some things you'll notice, there's a lot in the Mid-Atlantic, and certain clustering in certain states. So Colorado has an additional state tax support and Virginia and Maryland do that make it extra kind of an extra incentive to put your land into conservation easement. But so this is the kind of the constraint. And kind of the idea here is in theory, this easement, when you give up your development rights, not only are you giving up your right to develop condos on your forest or your farm, but you're also giving up the right to put windmills or solar on it, right? So it's restricting any development. So you can think of these as areas where you can't develop wind or solar transmission projects, or if you did, it would be very, very costly and legally tenuous. So if we put all 3 of these together, right, we see a lot of land use restrictions and where we can do this, right? Think of that map before that kind of had that blob of like, we're going to have a bunch of wind and solar, right? And when we take into account all the wetlands, all the conservation easements, all the endangered species protections, right, it looks a lot more patchwork and difficult, especially when you need to do linear projects that involve transmission that go across areas and aren't just in a particular parcel. And to zoom in on a few areas, just so you can kind of see the scale, this is Massachusetts. Can kind of see the boundary. Gray area places that are developed or have an impervious surface, so that's Boston right there. As you can see, it's largely dominated by these small wetland features, these blue areas, right? You kind of see these all over when you drive. And then also kind of conservation easements in orange are throughout. And you see a few kind of larger swaths of Endangered Species Act, and there's a few other areas of red that are quite small, but scattered throughout. And then the purple are where there are today windmills or solar PV stations. So it's kind of hard to see in this projection, but there's a handful throughout. But you think of siting this, right? You kind of got to avoid all of these things. Go to the Bay Area, it's a very different story. So this is San Francisco. This is Silicon Valley. This is Berkeley, right? You have a ton of Endangered Species Act restrictions in red. You also have conservation easements kind of in the mountains of Marin, and then kind of some wetlands throughout the bay. And you'll see here, we have this big pocket of wind development right here and some more here, but it's also kind of in a very different set of land use restrictions affecting development. And then here is a different example. This is Dallas, Texas, right? And it's a lot easier to potentially develop here from a land use restriction standpoint, right? You have some easements in orange. You have some Endangered Species Act, not as much wetlands unless you go into East Texas. And because of that, then potentially because of that, you see then wind and solar, in a lot more places, that has the space to do it. Okay. Speed up a little bit here. So I'm going to take all this. This is the kind of the data that we're going to now merge and map onto. Put yourself on the hat of I'm a real renewable energy developer. Where am I going to put my site? Okay. And so we're going to leverage this kind of interesting feature and database called interconnection queues. So I'm a developer. I pretty much figure out where I want to go. I get site control, right? So I either get a lease on a piece of land or buy it outright. And then I do some technical work. I say, okay, I think I have a project here. And then I go to the local balancing authority, the local ISO, the local whoever the kind of like the agency in charge of transmission. I say, I want the right to sell my electricity into the grid, right? Because ultimately you need to plug into a transmission line and a grid, or you're not going to be able to sell your solar or wind power. And this is going, and then once you receive that, then you can start designing and building and commissioning and operating your plant. But you're not going to do that unless you get the right to sell into the grid. So this is the setting that we're going to use. So kind of what this is all projects that entered interconnection queues in the US over the last 2 decades. So as you can see here, some interesting things is this other includes natural gas. This includes like all other fossil fuels. Like ever since 2015, the vast majority of new projects trying to enter the market in the US have been solar and wind, and increasingly recently battery projects, which are often related and hybrid systems with solar and wind ones, right? So the interconnection queue these days, the people developing projects and trying to sign up for to get into the grid are renewable projects, right? And it's this huge mass that I talked about, but because of that, there's a lot of weight, right? This is gotten where there's a lot of congestion in this line, and it can become an impediment to like whether the project economics can work or whether you can successfully develop your project. And the kind of spatial extent of projects that ever enter this queue are right here. So it's kind of throughout the US, and some of the broad patterns match what you might think. We know kind of wind resources are strongest in the Midwest, solar resources in the Southeast and in parts of the Southwest. And we can observe about 28,000 projects that at some point requested interconnection, and about 2/3 of these are wind and solar. So we also want to know, like, okay, who entered the project? What determines where someone would try to get in? So to do that, we have to kind of develop potential projects, almost like placebo points of theoretical ones where someone could, but then ultimately didn't decide to apply for an interconnection agreement. So what we do here, just take an example state of Pennsylvania. I just kind of randomly produce dots, 100,000 across the US, and then filter for some obvious ones. I'm avoiding federal land, open waters, national parks, and then just saying like, okay, this is a dart on the land. This is theoretically somewhere that could be developed. What determines where the blue points are, where people actually tried to enter the queue? And then in a second stage, or the black points, sorry, and then in a second stage, who actually, of the black points, who actually ended up getting an interconnection agreement? So this is the kind of like setup of the data that we're going to use to try to assess what determines project success. And what does this pipeline look like? This is kind of for wind example. You know, I randomly throw 100,000 points on the map. I lose about 8% of them to they ended up in open water, some obvious reason you wouldn't develop them. We end up with 92,000 hypothetical points. Of that, in our Q data set, we observe about 4,000 wind projects of someone at some point wanted to develop a wind project at this lat long point. And then of those, about 40% ultimately ended up getting an interconnection agreement, right? So succeeded. The other ones either withdrew or failed or are still active. And then of those, about half are operational as of today, and others are still in the queue. So this is the pipeline. We're going to try to understand what explains which projects succeed and which ones don't throughout this. Okay. So now we're going to go to land use policy. We talked about these kind of hypothetical measures of conservation value. Not hypothetical, but like, you know, in the ideal world, this is what we're trying to protect. We're trying to protect species, we're trying to protect wetlands, we're trying to protect ecosystems, but kind of on the books, we actually have policies that try to approximate, you know, get at those conservation values, and that's what we're going to look at now. So I again won't go too much into this, but kind of a big part of this project was pretty much modeling out the economics of every single development project. You know, from a profit maximization standpoint, what determines whether I would enter, or whether I would do a project or not? Kind of in a nutshell, I can model profit of a given project on the price I would get for my electricity times if I get tax credits times the amount of electricity I would be producing, which is further a function of curtailment rates and resource potential. Then I have to take into account my investment costs, you know, my CapEx, and then there's also transmission interconnection costs. You have a project, and then you get interconnection to the queue. They're going to say you have to pay $2 million to expand the line and upgrade the substation in order to sell into it, right? So that's another cost you have to take into account. And then there's direct land costs, whether you're leasing or buying the land that you have to take into account. And then there's all these other things that aren't conventionally modeled in these capacity expansion models, right? Which we're going to think about here. This, you know, sum over X of all these other things. And these are all the things: land use restrictions, permits, conservation easements, et cetera. Yeah, John. Yes, yes. So we are trying to model it. I mean, so to say that back is another cost is, you know, this congestion in the queue, such that like you can't get an interconnection agreement immediately, right? It represents a real economic cost and uncertainty to your project that should, you know, go into this profit function. We don't get at that yet, but there's some ways we try to, which I'll get to. But yes, that's an important point. And a lot of the interconnection queue reforms that are happening through PJM's, kind of the major one in the Mid-Atlantic, are aimed at trying to like streamline this process to reduce delays and how long it takes you to get a interconnection agreement, and to batch projects so it's not kind of this one-off thing. But that's a major thing that utilities are focused on. And so these decisions are happening in two stages. So first, what is my expected profitability of entering the queue? Like, should I propose a project and go into the interconnection queue? And that's going to be a function on Z, which I just bucketed all these kind of stuff that we conventionally see in models into this Z, and also this X, which is the stuff we're going to talk about today. Right? And we'll enter if our expected profitability, our profit is over 0, and then conditional on queue entry, the interconnection decision, right? Do I stay in and do I get the interconnection agreement and like kind of agree to pay and do it, right? Do I move forward with my project, right? Is a similar function, depends on project economics and all these other factors, but it's updated with information since then. Right? Project economics might have changed. Your PPA might have changed. Your technology costs might have changed, right? You might have learned more about siting constraints. So we're going to use a sequential selection model here to account for the fact that the errors in those two stages might be correlated, right? And if they are correlated, then if we're just estimating that second stage without taking into account the first stage, it might yield biased results. And so I won't go into this now, but we kind of leverage the fact that technology costs and PPA prices from the entry stage, we exclude those in the next phase of our model. So gosh, in the interest of time, I'll keep going. So CapEx is a big part of this, and to model this out appropriately, you have to understand what is the right capital cost to assume for a windmill of a given year, right? Because the physical capacity and costs of them are changing by technology, wind, solar, whatever else, and by region, right? There's some modeled estimates of that, and kind of you'll see over time the capital costs of wind has decreased, but it's kind of quite complicated as the technology and locations of wind have changed. And then a lot of the bulk of our modeling happens on calculating the expected project revenues, which again is how many electrons are you selling, which is kind of this factor here, a curtailment adjustment factor, and this is really big in wind and solar, right? Particularly where like all the wind's blowing in the Midwest at the same time, and if there's congestion or like they can't use that electricity, you got to turn off your wind in a way that is different with fossil energy. So this curtailment estimates can have a big effect on your project economics. And then the power purchase agreement. So this is going to be region, technology, year. Those prices will often take that into account, right, in terms of like the reliability of the electricity that you're selling. So this is kind of your long-term agreements of what utility or end user is going to purchase your electricity for, including RECs, renewable energy certificates, and then any tax credit value. So that all kind of goes into our expected revenue. And then so that's our economic side. And then how do we measure our land policy side? Well, here we use like super granular spatial mapping. And so this is an example wind project in the interconnection queue that I pulled from Lewiston, Wisconsin, right? So it's right here. So some developer said, hey, I have a windmill, I have a turbine I want to build right here. And they go to the local authority and say, I want an interconnection agreement, right? So what we then do is compute a circle, a radius. We can vary it, but we start with about a 3-kilometer circle. And then we compute the area within this circle that is either in habitat for Endangered Species Act, blue for wetlands under the National Wetland Inventory, or orange for conservation easements. This is a nice example because it has all three in it. Not all projects do. Some projects have none of this stuff around it. But then we have a measure from 0 to 1 along each of these measures of the intensity of the potential exposure to these policies. And it's worth noting there's some noise on the geolocation. So it's like, there's two spatial things going on here. There's some noise about where the projects actually will be, especially if it's a wind project and there's multiple wind turbines, right? So where exactly it will overlap this, and then as well as the direction that the transmission has to go to interconnect, right? Which you also have to take into account where you'd potentially violate some of these land use restrictions. So this kind of spatial average of saying just like in the environment, in the spatial environment of this project, how much land use constraints are these projects facing? And here is from where I'm from in Virginia, just to show some of the variation in kind of our what we're going to find has this big effect of easements. So these are 4 proposed projects in an interconnection queue in central Virginia. You can see this is Charlottesville right here, if anyone knows the area, right? And orange is easements. This is a place with a lot of protected land and easements, and you can see, right, some of these projects might have trouble getting developed just based on the proximity of these easements, which restrict development of commercial types of development, including kind of transmission lines going through. So we put this all into our model here. And here's the kind of approach, the kind of what you'd say like the restricted model, how it would be if you were just an energy capacity expansion modeler, and you're not taking into account kind of these conservation policies and land use policies, right? So we're just going to include capital costs, right? That's our CapEx. That's our annual revenue discounted back. Transmission distance, you can think of that any given point. How far are you in kilometers from the nearest 69 kV transmission line? That's the kind of like minimum size transmission line a decent sized energy project has to feed into. Land value and development share. And then in the columns here are how do these things affect whether I enter the queue at all? And then when I enter the queue, whether I succeed in receiving an interconnection agreement. And then this third column is the sequential model that takes into account what's the probability of receiving an interconnection agreement conditional on entry. But kind of the intuition here, just to walk through quickly. Oh, and we also include ISO and year fixed effects to account for kind of different spatial and temporal trends. But this kind of fits the intuition. So this is for wind projects, and we see this negative coefficient on this binary outcome of entry, right? 0, 1, is there a project there trying to be developed or not? A negative 1, right? That makes sense. More expensive projects, less likely to enter. More more higher revenue projects, more likely. Negative coefficient for transmission distance further from a transmission line, less likely to enter, right? And kind of so this all kind of fits our intuition. It also kind of works in our second stage in terms of the negative and positive relationship in terms of the economics here. So like this is what kind of the profit maximizing developer would be taking into account when they do it. And then if we include in our additional land use and conservation policy scores, we can estimate those as well. So wetland share shows up as quite negatively significant here, which means in areas with more wetlands, you're less likely to ever see a project, right? Developers, and you can anecdotally talk to a developer, like they avoid wetlands if they can, right? I mean, it's a salient feature that's mapped, that makes sense. Endangered habitat, we don't see, there's no clear relationship there. And then here's the interesting thing on these conservation easements. We divide this into 2 buckets. Is there an easement right where the point is, right? So within 100 meters, right? And then this larger measure, what's the share of easements within 3 kilometers? So this kind of was an interesting finding here. For entry, developers appear to acknowledge they're not going to secure a piece of land that has an easement on that restricts what they can do, right? They're going to avoid properties with easements, and that makes sense. But then once you're in the queue, the thing that has the big effect is the neighboring easements, right? That's what predicts whether your project's going to fail or not. Where you might have been able to observe, like, okay, my piece of land is unencumbered, but if you have neighbors around you with easements that can potentially either slow down your projects for community opposition, or directly you not be able to do it because you can't get the transmission extension line to where the grid is, then that is the factor that's killing off the projects. And wetlands are interestingly also negatively affected whether you're gonna succeed. So those are observable in theory too, but kind of what we've seen in the Clean Water Act literature is wetlands aren't as obvious as you'd think. There's a lot of regulation changes in what constitutes a wetland or what doesn't, and you can pretty much discover a wetland nearby that you didn't necessarily think if you just did kind of spatial mapping of where it is. So these things are kind of like, in any way that we model it, consistently show up as this thing that predicts where projects will both enter, and then when they do enter, where they fail. We can run a similar analysis for solar projects and uncover wetlands are a little less relevant there, because in general wetlands are in places with, or solar projects are in places with less wetlands for perhaps intuitive obvious reasons, but we see this exact same relationship with easements, right? So developers are avoiding where easements are on their site, but it's these easements kind of in the neighborhood that are killing off or making projects fail. And kind of the general results, using our sequential model tell a relatively similar story, but also kind of pick up some of the wetland effect as well. Okay, so those are the results. One might be worried that our measure of easements is just it might all be in Massachusetts. We might have some spatial clustering of where this effect is, and it's not actually kind of a broad effect, or it's taking into account some other factors of the land like wetlands, because places with wetlands have more easements, right? Those are places where a landowner might want to conserve. So this is just kind of a residual variation analysis where I take my actual observed, was there an easement binary within a project site radius, less my predicted, I try to predict whether there was an easement based on all my covariates, things like wetlands, things on Endangered Species Act, things like land value, developed share, cropland, whatever you want, and then look at that variation. And kind of what you see both in our kind of placebo of all potential projects and then those that actually entered the queue is there doesn't appear to be major spatial clustering where it's all happening in one region of the US or not, or one state. There's kind of differences between green to blue in almost all the states where it's like some places these factors do or don't explain where the easements end up. So we're fairly convinced that the easements are getting at something in themselves and not just something related to these covariates or something that's geographically in just certain places. And then when we look at model fit, we actually do pretty good on predicting outcomes. So in terms of projects that enter and all of our potential projects, we predict that about 4% of projects enter when we kind of run it with our model. And in the data, we see the same thing. And from a 1-by-1 project, if we just predict it using our model, we get about 96% accuracy. And then once a project has entered, will they get an interconnection agreement or not, right? And for wind, about 26% of them do. We find the same mean value. And of those, about 79% of them we get right with our model. So our model, with the incorporation of these land use constraints and projects, does a lot better than just the economic model in predicting where projects will go and whether they succeed. And for solar, it's a kind of similar type results where our mean values are the same, somewhat by construction, but we get pretty good percent correct in terms of predicting it without kind of knowing anything. We just know like where this is, whether the project will succeed or not. Okay, so to wrap up very quickly on the cost benefit implications here. So we're going to run a little simulation. In 2011, the RPS, the Renewable Portfolio Standards, pretty much said to states like, here are your renewable energy targets. We're just going to take these as binding exogenous, which isn't fully the case, but and just simulate project siting over that same time period under counterfactuals where we just take out land use constraints. We say like, okay, let's forget about wetland constraints or easement constraints or anything else and see what would have happened. The kind of the steps here is we're going to sum renewable energy generation across all the interconnection agreements in gigawatt hours in each state or ISO. We're going to use our two-stage probit to identify the most likely locations for these investments. And then we're going to simulate it based on these same project economics, the same kind of type, megawatt hours and timing and features, but then remove these protections and then compare the differences. And kind of what we see here is that if we remove, this is for wind, if we remove wetland protections, right, this affects where about 1.7% of projects, right? Like you either won't or will get, right? So it affects a little, not much, under 2% of projects, these wetland protections are affecting. But if we remove easements, a much larger share of projects get affected, right? Up to 16 or 17%. So that coefficient we find on easements in terms of the standardized value is quite big, and also kind of in the simulation shows that like we would have a different spatial mapping of where renewable energy would be, in the absence of easements. And then if we kind of compare what we care about at the end of the day are conservation values that we get from this exercise, right? That's why we have these protections. What do we see? We see if we removed wetland protection, our TNC impact score goes up by a large share, right? Impact is bad in this case from a conservation standpoint. So it's saying like we're developing more sensitive areas without the wetland protections. And that's just an index. And we're also obviously developing more wetlands because we have wetland restrictions. Not much noise on the Endangered Species Act habitat stuff. And then a non-significant effect on levelized cost. And we kind of see a similar type story with removing easements, where if we remove them, we do develop more. There's a cost of conservation value, right? We're harming conservation areas, but kind of the interesting thing in this very preliminary simulation, which we're still incorporating new things, is there doesn't seem to be a material effect on the levelized cost, right? So these policies seem to be shifting where projects are going, but it's not necessarily like as picking a much more expensive place or a worse project from an economic standpoint. So that's I would say the kind of potentially hopeful side, that these do seem to be working at some extent of protecting these areas, but not necessarily raising the costs. But that's more preliminary there. So I think I talked about that. So to kind of summarize, and then I'll open up for questions. Is there a tension here? Yes, there is. Right? The conservation values and LCOEs, levelized cost of energy, are uncorrelated, which means they're not systematically correlated, but at the same time, just in the randomness, you can, a lot of the low cost energy projects you have might also have very high conservation values. So we do want some sort of policy that protects those conservation values. Second, are land conservation policies impacting renewable energy project siting? So all those kind of headlines that we saw, right, that kind of environmental groups or environmental policies are killing off projects? Yes, there is pretty strong evidence that is the case, both for what projects enter as well as ultimately what projects get interconnection, and if they don't, then fail. But then when we look at the actual cost benefits of this, our preliminary analysis suggests that like by these projects failing, it doesn't necessarily incur much more of a cost in terms of the overall projects that get developed. So I will wrap up there. Thank you.
Great. Thank you, Charles. So we have a few minutes for questions. I already see one hand energetically in the air. Your office is about 50, 60 feet down the hall from mine. So I'm going to follow up with you later with my questions and comments. But let me go to the audience here first.
Thank you. Thank you so much for that fascinating presentation. I'm Margaret Williams with the Arctic Initiative in the Belfer Center. I have a comment and a question. Being from an Arctic state, the one Arctic state, I noticed that you're missing Alaska from your analysis, which has, of course, covers 1/5 of the United States, has tremendous thermal, solar, wind, tidal power, and also is home to North America's largest wetlands. So I imagine if you added that, that would provide more fodder for your analysis. But At the very last, in your summary, you mentioned that some of these conflicts do end up killing off projects. What about the current policy situation? The administration is the #1 killer, I think, of the hope for renewable energy development in the United States. We heard this morning that they're removing energy EV charging stations from federal sites. I mean, the federal funding is disappearing for renewables. So it seems like that is going to massively change your analysis. Not to mention the gutting of EPA, Clean Water Act, Fish and Wildlife Service, all of those agencies that are playing a role in protecting our lands.
Yeah, thank you, Margaret. So first on Alaska, point taken. I mean, I'd argue there's not as much demand for the energy up there. So, but we could certainly, I mean, right, all those things are true. So thank you. On the current administration, yes, like this, this is a big variable that will, I will eventually want to put on the right-hand side of my regression that, will change a lot of these probabilities. I don't, it's hard for me to empirically say what to do with that, but yeah, I mean, I guess I will say that, the fact that, these projects have kind of been linearly increasing for the last 15, 16 years under different administrations, and there's some momentum, and the project economics are what they are. Like, I don't think we're going to see it drop overnight. I think we're going to kind of see a trend shift down from what we'd expect, but I still think there will be growth, but I'd imagine it would be mitigated in that whether then these land use policies can be regulated and enforced through a change in EPA enforcement is another valid question.
Hello, I'm Sammy. Thank you for this talk. I'm wondering about if you are distinguishing between types of conservation easements and how we can think about, if a wetland or wildlife conservation easement holds a different value than agricultural conservation easements, and if this is represented, outside of this conservation value, or if we can still think of it within this TNC number, and how, ag conservation easements play a role in this.
Yeah, excellent point. I mean, that's a big chunk of this paper that I didn't get into today. Is just for background, right? There's agricultural easements, which are meant to kind of protect farmland in perpetuity, right? Protect our farms. And then there's more kind of conservation or ecological easements. And then there's a whole other things category that you can get the tax deduction for is historical preservation, right? You have some historically important landscape. We do find heterogeneity across these, and for example, wind and solar are also suggestively different, where it's more easy to put a farmland easement. You can't put solar on, but you can potentially put wind nearby, right? So you see some differences by the type of renewable there. But yeah, that's a great point.
Thank you.
So I have the 3 questions. So first is I would like to see on your final simulation projection of how much projects, how the number of project changes rather than costs. It's kind of unexpected or expected that the economic cost doesn't change much due to your previous numbers of the environmental value seems to be quite equal among these places, but yeah, so that doesn't change the economic cost, but it may change the number of projects get approved. Also that's a comment, but the 2 questions are the first, the difference between local easement impact on entry and neighborhood easement impact on interconnection probability conditional on entry. Does that suggest that project investors are doing a bad job predicting where projects can get approved? So they only do local check. Okay, so this place has an easement, so we don't do project here, but they don't consider kind of the interconnection probability or all those things. If so, yeah, probably that's suggesting, these projects, investors are not doing a good job. And the third thing is that does the result that conservation easement changes, removing that doesn't change as much environment score as the waterland, means like probably conservation easements policy are not as targeted and as valuable as water wetland kind of act.
Yeah, I mean, in the interest of time, those are all great points, and we can look into that, and we can talk at in my office. Thank you.
So given that we are about out of time, before we wrap up, let me note that we'll meet again at noon on Monday this coming week. We'll have Jim Stock subbing in for Elaine Buckberg for a talk about EVs and the prospects of EVs on the road ahead. Will the Trump administration stall adoption? Finally, please join me in thanking Charles Taylor for his presentation today. Thanks so much, Charles.
Thank you, everyone.